see, let's get rid of this tab. All right. Good morning. Oh, there we go. Good morning, everyone. Just trying to make sure I have the tabs correctly, and let me check to make sure the IPvo is, yeah, that's working. We're getting our nice springtime weather, good or bad. That's Houston. So if you like it, great. I always thought it was interesting to be in warm weather and have congestion. That was always something odd for me to get used to when I moved to Texas. Now, just remember that today, what we want to do is to discuss some models, basically the types of models that you did in your college algebra class and possibly in an Algebra 2 class. And after we complete the models, we would like to give a fundamental review of inequalities. Inequalities play a big role in calculus, and we often determine inequality solution sets by doing a sign test. And I want to be able to show you some techniques that will possibly make that um, uh, technique maybe a little bit easier. Uh, there's nothing wrong with a particular technique in mathematics, excuse me, if it gets us to the finish line correctly. But sometimes we can do things that can possibly make what we do more efficient. But efficiency, without correctness is no good either. So we want to reach that nice balance. So the first thing I want to do today, ladies and gentlemen, is to oh, good morning, everyone. You all are so nice. I usually don't have students who say good morning. So thank you, Destiny, Yarlene, and Jeremy. You all get your 5 bonus points, of course, to lift your morale. But I appreciate that. That's very kind. The first question that we want to do today is the one I left you with last time. And again, some of these problems maybe aren't of that great of an interest. Um, you do some of the problems in the 1.3 and 1.4 that just seem to be all over the place as far as just a technique of multiplying or factoring without a whole lot of result or goal in mind. And so maybe today with the modeling, it won't be as bad and maybe somewhat reminiscent of the problems you did in your college algebra class. So what I wanted to do is take several problems that should be familiar with you and work some new techniques possibly to make the work a little bit more efficient. Now, with this problem, a very simple problem, but I want to show you some techniques. We have Ben invest 4,000 at 4% per year. So I want to go ahead and just do some conversions. 4% is just 4 over 100. Sometimes decimals are good, sometimes they're not, especially when we want to let the mathematics do most of the work for us. And then it says, what additional money must he invest at 5.5% annual interest? So let's write that down. So 5.5%, we can write this as an improper fraction, and that will just be 11 over 2%. Again, divide that by 100. So that's 11 over 200. Now, if we're thinking common denominators, let's go ahead and get a common denominator and multiply and divide by 2, 8 over 200 there. And then it says additional amount at 5.5% annual interest to ensure that the interest he receives each year is 4.5% of the total amount. Okay, well, let's go ahead and write that as a fractional equivalent. So again, that would be 8 plus 1, so that would be 9 halves. And then, of course, we can divide by 100 the definition of percent. So sometimes when we're dealing with mixture problems, with with percentage type problems, fraction of work. The fractions actually make the work a little bit easier because they keep the arithmetic more simple. If we allow the arithmetic and algebra to take over and do most of the work for us. So now all we need is that additional amount. So we can say let X equal the additional money. Just give it a variable. So now again, he invests the 4,000 at 4%. So we have $4,000 invested at 4%, 8 over 200. And the additional amount, X, he invests at 5.5%. So this is 11 over 200 times X. And then we want the total amount invested to provide 4.5%. So 4.5% is 9 over 200. And then, of course, the total amount will be X plus 4,000. So the equation is fairly simple, but I wanted to show you how you can use fractions to make the work a little bit simpler. Again, it really doesn't matter how you organize your work, but think about explaining it to someone and saying, now, if I explain it this way, is my student going to figure it out? I was doing a problem yesterday in calculus, and I told them, I said, this is one way to do it. I said, but it's a little bit complicated. Let me adjust this a little bit so that it's easier to explain. And you think about it. If you provide an explanation, you want it to be something that the student can remember, or at least there will be something about the problem that motivates common sense. So now when we look at this, we see that everything has a 200 in it. All these 200s are just in the way. So what we want to do is multiply the entire equation by the least common denominator, which is 200. So this is kind of like doing the solving bit. So now we'll just do times 200. You can do this symbolically, but it's nice to just write down so you can go back and check what you did. So now all the 200s absorb. So we have 4,000 times 8 plus, and now of course the 200s absorb here, and we just have 11x. So we simplified things really nicely here. Now notice the same thing here. The 200s absorb, and we get 9x. And now again, the 200s absorb, and we get 9 times 4,000. Now what I'm talking about with the symbolic computation is that as we do the actual work, we can let the algebra do the arithmetic for us without always having to multiply everything. So now if we look at this, we're thinking, well, let's just get the x's on the left. So now we can subtract 9x's from 11x's to leave us 2x's. And then, of course, algebraically, we have 9 copies of 4,000, and we want to subtract 8 copies of 4,000. So that leaves us with 1. So here's a way of using the number theory and the algebra to give us a very simple computation. Again, this is just another technique that I think you might find useful, especially as you all start to tutor. Some of you may become tutors in the Student Success Center, or maybe you're already tutoring at your high school. But now when we divide by 2, x is 2,000. So this would imply the additional amount, or the additional money, is $2,000, of course, invested at 5.5%. Now, again, a very simple problem and maybe not an earth-shattering problem, but just a way to look at the arithmetic in a different way. Um, I had often have students ask me, for instance, they'll say, well, what should I review? Like in my calculus class, calculus 2 class, I found some end papers in the textbook. I said, this gives some great review of some algebra, geometry, and trigonometry. And I'll say that's good to have at your disposal. Another thing that students will ask is, do I need a particular type of calculator? Well, the Google calculator on the internet is a very nice way to do scientific calculation when you need it, and it's free. Um, Again, make investments into items that you think you might need and that will help you get better. But don't make investments into things that are basically going to do too much work for you, because the whole idea is to get you to improve that thought process. Now, let's look at another example. So again, simple but useful. And as you look through, of course, I record the lectures. As you look through some of the Smart Pen videos, you'll see some similar problems that I've worked as you need additional content for the class. Now, what I wanted to do were just some maybe simple geometric problems before we get, I think, to the a mixture problem. So here's an example. So we have a we've got a poster that has a printed area. I'll draw a little diagram. Printed area that measures 100 centimeters by 140 centimeters. And the poster, let's see here. Oh, and here's an additional. There's a uniform strip. Strip, I'll draw a picture. Strip of uniform width around the edges. Now there's going to be one more description line, but I want to go ahead and just draw a reasonable picture. That often nice to have a little diagram to organize your thoughts, just like what you'll probably do in calculus when you're trying to compute areas bounded by curves. It's always nice to have a inexpensive drawing that gives you ideas. Now, we've got this strip that has uniform length. So I'm just going to go ahead and mark off the strip so you can easily see what I've described. So just like a picture, you can think of the strip as like a frame. So we have this printed area. First, what I'll do, again, the strip, we'll just say the problem gives just a uniform dimension. We'll just call that X in this case. So I'll just say X centimeters. And we have X here, uniform all around. And then, of course, the printed area, if you will, this is 100 centimeters here. And then for this dimension, we have 140. So that's kind of the bare bones of the problem. Then one more description says this. It says the poster perimeter, and then we'll add a few more ideas here. The poster perimeter. I think this is busier more so with the words than it is with the algebra. The poster perimeter is 3/2 times the perimeter of the printed area. I'll go ahead and put the in there. The perimeter of the printed area. And so what we want to do is compute width of strip. So that's what we want to compute is the X here. So now what we can do in a way to make the problem a little bit simpler is now think about perimeter. So we have a perimeter of the poster if we think of 100 plus the dimension of X here and the dimension of X here. So if we go all the way across, we have 2X plus 100. Now, likewise here, as we go in this dimension, we have the 140, then we have the copy of X here and the copy of X here. So we can do the same. This will give us 2X plus 140. So that is a simple way to figure out what we're thinking of in terms of the length of an edge when we are discussing not only the poster, but also the printed area. So what we want to do now is use this description here to solve for X. It's just going to give us a bunch of numbers with an X in it, and we'll solve for X and maybe use some symbolic computation. So poster perimeter. Okay, so first we want the poster perimeter, and we want to set that equal to 3/2 times the printed area perimeter. So just following the guidelines of the problem. So poster perimeter, let me just write this down. Poster perimeter. That'll be the first thing we need. So we're going to say 2 times this dimension plus 2 times this dimension. So let's do that. So we have 2, so we have 2 copies of it, 2X plus 100 plus 2 copies of this, 2 times 2X plus 140. And now this should be equal to 3/2 the perimeter of the printed area. So what we can do now is have 3/2 and now do the printed area. So we'll have 2 copies of the 100 times 100. And we'll have 2 copies of the 140. Again, not like the last problem, not overly difficult, but something we just need to think about in terms of organizing our thoughts. If we organize our thoughts, then we can write down exactly what the problem describes and then let the arithmetic and algebra take over. One thing you'll notice, and we're going to be able to relieve ourselves of some of these factors because we've got 2's hanging out, which are just in the way. But the first thing here, we've got this 3/2. And notice if we do symbolic calculation, if we multiply by the 1/2, we can absorb this 2 and we can absorb that 2. So let's go ahead and do that first and just let the algebra take over without having to do a whole lot of work. So we'll just be court reporters. When I say court reporter, I'm just saying we're copying things, but we want to make sure that we don't make 2 or 3 mistakes in copying. So here the 2's absorb, and this leaves us with 3 times 100, just like we did on the last problem. And here the 2's absorb, and we have 3 times 140. Now, of course, there are more numbers here that we can get rid of, but we want to make it very, very simple. Notice again, just as one more exercise in reducing numbers, and then we'll just call it quits. We have a 2 here, a 2 here, we have a 2 here, and a 2 here. So let's divide the entire equation by 2. So I'll just say divide by 2. So if you want to write that out, you can just hit everything with a 1/2. Just to make the number smaller. So the 1/2 will absorb the 2. That'll be a 2x plus 100. The 1/2 will absorb the 2, leaving a 2x plus 140. And then, of course, the 1/2 here will absorb into the 100, giving us a 50. So 3 times 50 using the distributive law, and then the 1/2 absorbs into the 140 to give us 3 times 70. Now, at this point, you can look at this and say, well, we can make the numbers even smaller, but I think the numbers are real simple at this point. So you don't need to make any more divisions. Of course, we have 2's and everything. We could divide by 2 again, but I think you get the drift. And like I say, the numbers are simple enough that we can go ahead and move forward with the calculation. So now we've got a 2x plus a 2x. That's a 4x. Only because the numbers are easy. If they weren't easy, I would divide again. And here we have a 100 plus a 140, so that's a 240. And then, of course, here we have a 3 times a 50, which is a 150. And then, of course, we have a 3 times a 70, which is a 210. So now we can go ahead and do some simple arithmetic. We have a 4x. And of course, if we subtract the 240 from the 210, that will leave us with a negative 30. So we can go ahead and subtract that. Again, the numbers are real simple, just powers of 10. And now, of course, the 150 minus the 30 will give us 120. So my philosophy is if the numbers are simple enough, you don't necessarily have to reduce. I'll leave that up to you. But notice we just have very simple arithmetic. And now, of course, if we divide 120 by 4, we get 30. So this is an example of, again, not just multiplying everything out and getting numbers that are large. It's just a matter of letting the algebra do some of the work for you, where the numbers are very simple and we can easily combine them. Now, so in our conclusion, we would just say that the strip has width 30 centimeters. So we'll say strip has width 30 centimeters. Again, a very simple problem, but just a problem to get you to think about how you combine numbers and letters, because it's all the same. The number theory and the algebra are all the same. And again, just a way of looking at things maybe to make simpler and to help you as you start to tutor. Okay, so the next example that I want to do is a mixture problem. Now, again, mixture problems, time, rate, distance, fraction of work, they're all about the same. I don't really find that students find, when I think a student, I may feel that a student finds a particular type of problem to be easier. then they proved me wrong. I used to think that students liked the time, rate, distance, and they were the best at that, but it varies every term. So here's an example that you would have done in your college algebra class or even a algebra 2 class in high school. We have how much pure acid. So I want to show you some techniques to make these types of problems easier and less busy. How much pure acid must be added to 300 milliliters of 50% solution, and we'll say 50% acid solution, to produce a 60% solution. And I'll go ahead and write acid here, acid solution. So here, if you want to just write that in just to be sure, it's assumed, but sometimes it's better to go ahead and write this in. Now, with these types of problems, we're going to also do a problem having to do with a cooling system in a car, where the volume will be constrained by the volume of the radiator. But notice here we don't have that constraint. We're just simply asked to produce a 60% acid solution from a 50% acid solution. So what we can do with this problem is think about filling in blanks. First, we just use a variable. Let X equal the volume of pure acid. So we have a solution that we want to make more concentrated. So just like with all the problems we do, choose a variable at least to define the quantity that we do not know. Now, here's a technique that I developed when I started teaching. When I first joined the San Jac North math faculty, I actually taught, Nate Wiggins and we taught half in college prep and half in academic. And so I came up with these techniques to teach the students in the intermediate class that we taught at the time. It was Math 0306. Now it's been changed. But they enjoyed it because they thought it was simple and easy to teach. So I'll let you all be the next group of kids that sees this. Again, this is just a simpler way, I think, of looking at it. So if we think about what we're doing in the lab, we have a 50% solution. So I'm just going to label it here. This is not part of the computation. It's just a little label, so you can put it in parentheses if you want. And we're going to add some 100% acid solution. And the goal should be a 60% solution. So this avoids unnecessary calculations. Now, this is why I like using the fractional equivalence for the percents, because we can always eradicate the denominators to make the numbers really small. So first, we just go ahead and draw the actual percentages. 50%, which is 50 over 100. 100% is just 100 over 100. And then, of course, 60% is 60 over 100. And so what we want to do is have a preservation of acid, so to speak. So when we look at the original problem here, we have a concentration times the volume. So how much acid do we have in the 50% solution? Well, this will just be times 300. And then we have to add the unknown amount. So what's the volume of the pure acid? That will just be X. You can put a little dot there if you like for multiplication. It's of course not required. And then here, this is where we say, okay, well, we're not constraining the volume. So we get the acid part that we add here to the additional, or to the actual beginning volume, which was 300 milliliters. So when you think about this equation, this covers all the bases. I see very interesting techniques with these problems that that make the problem harder than it is. And so I'm not always sure why there might be some techniques that a student would choose, but I just remember at the time that this would be a way that the students could share ideas with each other, and it seemed to be a very simple way. Remember, I'm just using these as blanks. So now we have an equation in terms of x that defines this situation, one equation. Just we'll do the same when we do fraction of work. And so now, first thing we notice is that just like with the interest problem, we have all these 100s. We'll just get rid of them. You don't have to do this multiplication by 100 like I'm doing, but if I don't do it, you won't think about it. So maybe do it. So now, of course, the 100s absorb, and we're going to let the algebra do the work for us because we're lazy. So I put the dot here to avoid excessive use, excuse me, of parentheses, but don't think of this as a decimal. Place it up high enough so you know it's juxtaposition, multiplication. And now, of course, the 100s absorb here, and we just have 100x. Now with the 100 here, notice only thing we're left with when we multiply by the 100 is the 60. So we get 60x plus 60 times 300. So this is what I was talking about last time with the interest problem. The numbers that, I mean, obviously we have some common factors here that we could use to make the numbers even smaller. But the thing is, the numbers are so easy. Don't worry about it. You know, there are times when we'll say, oh, look, we've got a 17 in every number. That's a prime number. We need to clean it out kind of thing. But notice here, the numbers are so easy, we can add them algebraically. So now we'll say, well, we have 60 copies of X that we subtract from 100 copies of X. That leaves us 40 copies of X. Again, very simple arithmetic. And notice here, from the 60 copies of 300, we subtract 50 copies of 300. So that leaves us 10 copies of 300. Now, if you like, you can just go ahead and divide by 10. So this gives us 4x equals 300. And now we can divide by 4. These are easy numbers. So we have x, and 300 is just 4 times 75. Divide by 4, and we just get 75. So you can see here that the simple way of dealing with percentages is made easier thinking of them in terms of fractions. And now you can see that based upon what we got for X, that we need to add 75 milliliters of pure acid to obtain the 60% solution. So this just says add 75 milliliters of pure acid. So again, this is just a very simple way of thinking, okay, well, you know, when you look at this kind of problem and you think about what we're doing here, this simply showcases the problem with one equation, attacking the concentration. Maybe the concentration might be dollars per pound. Maybe you're working in Starbucks and you're trying to make a new coffee blend. It's the same thing. The concentration can take on many different characteristics, and then you'll have some volume or some weight of something. And so that's the same technique that you apply to all the mixture problems. And I think this makes it very simple. Again, add this to what you already know, but it is surprising when I see students work this problem and there appears to be absolutely no logic behind it. And it's more convoluted than this. So think about these techniques I'm introducing and maybe think about modifying how you look at these problems. So again, very simple, but we let the algebra do the work. Now, the other problem that I wanted to mention was about the car radiator. I thought this was an interesting problem. Let's see here. Okay, I don't understand that, but whatever. Sometimes when you all abbreviate things, I don't know what that means, but that's okay. You must have a conversation that you all do amongst yourselves. Now, let's look at the next example. So we have a car radiator filled with 60%. Oh, I get it. NP means no problem. Okay, well, I'm not so square that I get it. Now I get it. All right, whatever. I have to remember you all abbreviate things like I do. 60% antifreeze. And then the manufacturer has to step in and say a few words for optimal cooling. So, you take your vehicle in or you go to a business and you do the algebra for them to make sure they are charging you correctly. For optimal cooling, 50% antifreeze is suggested. Of course, in the WebAssign, these are written, and as you read problems that I've done, a lot of times with the Smart Pen videos, I write out the problem. And I'll just say the radiator capacity, this is what I was talking about before, the radiator capacity is 3.6 liters. Then it says, how much solution, you'll see how simple this is, how much solution should be drained and replaced with water. So again, maybe not the most interesting problem, but maybe you're just an engineer at heart and you work on your vehicle. I've had students before who take engines apart and they do these types of services at home. They've got a garage set up and that's great. I just go to Norman Frady and they take care of my truck, but because that level of expertise I don't have time to cultivate, so I let them do it. But you can certainly do yourself a big favor if you already have the know-how. So this again is a college algebra problem. So when we look at this, we want to make the antifreeze solution more dilute because it suggested that this is better for optimal cooling. So again, when we start the problem, we'll just say let X equal volume of replacement water, so to speak. So we have to get rid of the same amount of solution and replace it with water. So how you want to describe this is up to you. They're one and the same. So again, you're thinking concentration, amount of acid, but water doesn't have any acid in it. So that makes this problem so simple. So if you look at it in terms of the blanks, that is, we have a 60% solution of antifreeze. And then we're going to add water. And so this will be a 0% solution of acid. and the goal is 50%, which is what the manufacturers suggest. So this blank, we could just think about leaving out altogether. I mean, it's not going to have any impact, but I want to make it parallel to what I did before. So now you're thinking, okay, we have a concentration of 60%, so that's 60 over 100. We have a concentration of 0%. Well, that's not very difficult. And then we have a concentration of 50%. Now, just to make this a little bit simpler, we'll say 3 6/10 liters will just be 3, in this case, divide by 2, 3 over 5. And so when you write this as an improper fraction, this is just 18, 15 plus 3 over 5 liters, just to write this without the decimals so we can take advantage of the fractional arithmetic. So now when you look at this and you think about this, we're going to take away X liters of this amount that we have of the 60% solution. Of course, we're assuming that the radiator is full, so that we can assume. So we will have 18 over 5 minus the amount we drain. And then, of course, we're going to add X liters of water, but that has no acid in it, so this will not have an impact. And then when we look over here, we're adding the water, and that will give us the required amount, 18 over 5 liters. So when you think about this problem, we add water so that we maintain the volume of the radiator, but the water has no acid in it. So when you think about preserving the amount of acid, we're doing that. And it's important that we have this zero term here. Some students just leave it out, but I don't think they know why they're leaving it out. So here's the reason that that's true. And now when you look at this, the first thing we're going to say, okay, we've got a nice simple equation here. We can just go ahead and eradicate the 100s. So let me just go ahead and take the equation away from the blanks, just so you can see it a little bit more easily, since we've got some interesting numbers here. So I'm just going to remove it from the blanks. This is a nice example. So 50 over 100 times 18 over 5. So just as a simple way to get the ball rolling, if you will, let's just multiply everything by 100. That's the most obvious thing to do, and that's why the fractions make it so much easier. So we'll get 60 times 18 over 5 minus X. And then the 50, or excuse me, the 100s will absorb. And so we have 50 times 18 over 5. Again, we're going to let the algebra do the work because we're lazy. Now notice here, we have a negative 60. So I'll just say 60 times 18 over 5 minus 60x equals 50 times 18 over 5. So now we can let the algebra do the work, thinking in terms of copies. The 60, again, you can divide by a 10 if you want. I mean, let's just look at this. We've got a 10 here, we've got a 10 here, and a 10 there. Let's live on the edge. Let's go ahead and get rid of the 10. Why not? That just live on the edge, right? So 1/10. So this will give us a 6 times an 18 over 5 minus 6x equals 5 times 18 over 5. That's even easier than we ever expected. Now notice we can take 5 copies away from 6 copies of 18 over 5, and that'll just leave us 1 copy. Don't have to worry about any horrible fractions, and then add 6x to both sides. So if you let the algebra take over with the amount of work that you have to do, then you don't have to introduce a lot of decimals. And this is so much easier to teach, and you're going to help your friends understand this better. This is a simple problem if you set it up in terms of the concentration of acid. Now we can see that we can easily divide. So x, 18 is just 3 times 6. So we have 5 times 6. And of course, the 6 is absorbed, and we're left with 3/5. So now this just says drain 3/5 liters of solution and add, well, when I say solution, the 60% solution, and add 3/5 liter of water. So this might be a calculation. Maybe if you take this vehicle into service, they may have a little computer program where they enter the parameters, and the program will spit out what needs to be drained and added. Or you could just take your notebook and do the calculation on the side. But the idea here is that, again, this is not an earth-shattering problem, but the techniques that we use are important in that we can often use some algebraic symbolic computation, which is going to help you considerably as we work through this course and also in the calculus. It is often the case that students in calculus struggle with the prerequisites, not with the concepts. The struggling has to do with the manipulation of equations, the trigonometric identities. Trigonometry is extremely challenging if you don't learn the foundation. And so when you get to calculus, we want to make sure that all of that material is solid in your brain, and that you have confidence, and that when you see it, you know exactly what to be able to do to finish that problem, to get to the finish line. Now, what I want to do, remember I started the class with a fraction of work problem with the tankers. So I wanted to do another fraction of work problem that had 3 contributors. Again, it's going to give us a very simple equation to solve, but I wanted to take the technique that I introduced with the tanker problem and then apply it to a very similar type of problem. So this is a fraction of work. And here we have Jack, Kay, and Lynn deliver flowers. So that's the job, excuse me, deliver flyers, like flyers, advertisements. That's the job. So we say Jack, Kay, and Lynn deliver flyers. So this is the job, so to speak. I'll say job. The job is delivering the flyers, whatever that may be. So keeping it fairly nondescript. Now, what we want to do is write down what the problem gives us. And here's all the hypotheses. So we'll just say here, the first set of hypotheses have to do with working alone. So you did the job by yourself. And we'll say for Jack, the hypothesis is 4 hours. So that means 1/4 of the job per hour, okay? for K, we have T hours. That's an unknown. So we say 1 over T of the job per hour, the fraction of work per unit time. And then Lynn, I'm doing this in an order so it's easy to see. And of course you read this, but I'm writing it in the way that you should write it when you work these problems. Lynn actually takes 1 more hour than K. So she requires 1 plus T. So she can get 1 divided by 1 plus T, fraction of the job per unit time. So in this case, T, we say time to complete job for K. So what happens with these problems is that they'll just say, well, it takes Lynn 1 more hour than it takes K. So then you're thinking, well, I don't know how long K requires to do the job. So that'll at least be an unknown. Okay. So that's how the problems are written. You know this. And so you get to introduce a variable of your choosing, and we'll use T for time. And then we have one more piece, working together. They all work together. And the time to complete the job is 40% of K's time. So we'll say complete job in 40% of K's time. So what does this mean? This just means 40%. So we have 40 over 100. And again, you can divide, this will be 2/5. So equivalently, 2/5 K's time, 2/5 T. So when it comes to thinking about how we set up the equation, when they all work together, that's the amount of time that it takes. Each person works this amount of time. Again, that's the hypothesis of the fraction of work. You know, we have to make these assumptions or we can't do the problem. And then it says, of course, we want to find T. So compute time for K to complete the job. Now, of course, this problem is more complicated than the tanker problem. That's why I wanted to save this for later. Some of the problems are so simple, they don't even require a knowledge of college algebra. This is a college level class, and so we need to make sure that we're doing problems that are up to that level. So now when we think about this, we've got 3 contributors and we know the complete job is 100% or 1. So let's write it down. So just like when you do the blanks for the mixture, we'll have, and I guess we'll just do it in order. We'll say Jack, he will contribute some fraction of the job. K will contribute a fraction of the job. And Lynn will contribute a fraction of the job, and the whole job is 1. So the 1 is always over here. So we go up here for fraction of work. For Jack, we have 1/4. For K, we have 1 over T. And then for Lynn, we have 1 over 1 plus T. Now, when we notice here, and this is why I was careful to put a box around this. When they all work together, each of them work this amount of time. So we have fraction of work per unit time times 2/5 T. Fraction of work per unit times 2/5 T. And likewise here. So now we can fill this in 2T over 5. And we don't want to really factor this because we want to simplify these terms and then compute T. So these are the times each of them works when they do the job together. So again, don't factor this. We want to reduce this as much as we can. Then we've got equations with fractions and then clear it out and solve for T. So what does this give us? Well, first we see that the 2 absorbs into the 4. So that's going to be a 2 times a 5. So this is a T over 10. Here the T's absorb and we're just left with 2/5. So it's interesting when you look at this problem, it's just like what we did in 1.5. And now here, this is like a nightmare. Nothing absorbs. So we have 2T and we have 5 times 1 plus T. So that was kind of the nightmare expression where we don't get anything to absorb. Now we're back to college algebra where they say solve for T. And so now you just want to get rid of the denominator. So we look for the LCD, which is easy to compute. So this is a nice problem. So now, of course, we need a 5 and we need a 10. So 10 will take care of the 5 and the 10, and we need a 1 plus T. So we have 10 times 1 plus T as the LCD. So let's do that. So if you like, this is 10 times 1 plus T, 10 times 1 plus T. So good. What's nice about the models is that they use all of the nice ideas that we've already set up about solving equations. So we get to do our algebra. So now when we look at this, we see the 10s absorb and we're left with T times 1 plus T. Again, the 10s absorb. And now when we look at this one's kind of, well, not the best. The 5 absorbs into the 10 to leave us a 2. So this will give us plus 2 times 1 plus T. Again, remember here, the 10s absorb and we're left with T times 1 plus T. The 5 absorbs into the 10. And again, here's another thing that you already noticed here. I already had a 4 there, so I can't get rid of that. Or a 2, so that's a 4. Very important. So the 5 absorbs into the 10, so that's a 2. So I get a 2 times a 2, which is a 4, times a 1 plus T. And now here we hit the jackpot. Notice the 5 absorbs into the 10 to give us a 2. So that's going to be a 2 times a 2T, the 4T, and the 1 plus T absorbs. So we get plus a 4T. So all this is done symbolically. And now over here, we can go ahead and multiply this. That'll just be a 10 plus a 10T. So it's really important when you do the symbolic that you don't forget what's already in the numerator. Always go back and check to make sure that everything absorbs appropriately. So we have the 2 times the 2T. So that's the 4T, just like we have with this particular term. So now let's collect everything. So we have a T squared plus T plus 4T plus 4 plus 4T equals 10 plus 10T. Now, when you look at this and you think, well, what can we do with this problem? We can collect everything and see what we get. We only got one of the t-squared terms here. So let's go ahead and put everything together. So we have t squared. And then notice here we have a t, a 4, and a 4. So that's plus a 9t. So we can check all of these off. And then we get plus a 4 equals 10t. I'll do that first, plus a 10. So now this is going to be a simple quadratic. So now we can subtract the 10t from the 9t to give us a negative t. And then we could subtract the 10 from the 4 to give us a minus 6. So if we had just started the problem right here, ladies and gentlemen, you're like, oh, that's the least common denominator problem, knock it out. But what we see is that we had to do a whole lot of extra work to set this up. This is a good problem, but as far as testing goes, this would take study to master. So that's what I'm trying to show you here. If you want to understand how to do these problems and to teach them, then you've got to get at the heart of what's going on and not just memorize some little tricks that don't really tell you what's going on. All of this discussion here is exactly what the logic is. And so now you're thinking, okay, well, we can use Professor Ron's AC lemma. So if we do AC, that's just 1 times a negative 6. Well, that's going to be a negative 5. So we can just factor the negative 6. This will be easy as negative 2 times a 2. And of course, those sum to negative 1. So we don't even need that. We got the negative 3 and the 2. So equivalently, we have t minus 3 times t plus 2. When it's that simple, we don't even have to factor by grouping. Okay, so now what does this mean? Zero product if and only if t equals 3 or t equals negative 2. And of course, the negative 2 for the time does not have logical sense, so we discard. We discard this one. And therefore, what we see, and notice here, I was careful to choose the t for k so that we get it directly. We don't have to add 1 or anything. So that's what we need. Compute the time for k to complete the job. So k, this implies k completes the job in 3 hours. So again, what I want to show you here is just a technique that you can apply to simpler problems. You can use the same technique for this for any fraction of work problem, just like the mixture problems. They're all the same. There's no difference. There's absolutely no difference. The logic that you apply will be the same. The problem may be longer if there are more people contributing to the job. That's the only thing that we have here. And of course, it was a little bit more convoluted how we were given the hypothesis. So the equation that resulted when we did the tanker problem, that had fractions in it, but it didn't have as many terms. So the solution was easier. Here we have the LCD, and then we have to be careful about absorbing terms and keeping track of numbers. So this just took a little bit more vigilance in solving, but not anything any more difficult than what we've already done, just a longer problem. So hopefully this will give you some additional techniques. And as you teach this to friends who may be struggling with these concepts, you can help them with the logic. Excellent problem. And that's right out of your book. I'll say the Stewart Pre-Calculus book is one of the best. There is no perfect book. There's no perfect professor. There's no perfect student, clearly. What we try to do is do our best work. And I think Dr. Stewart, even though now he is deceased, certainly came up with an excellent book to prepare you for the calculus. Now, what I want to do is just a simple problem with the time, rate, distance. I leave this for last because I think what you're figuring out is that Professor Ron thinks the time, rate, distance are the easiest, and I think they are. So let's look at an example here that we can work on from your WebAssign. So enjoy these problems. These will be fun. You can discuss these, bring your questions to conference hours or discuss these amongst yourselves as you work through problems. So here's the hypothesis. We have Wendy is traveling. So we have a trip from Davenport to Omaha. Trip from Davenport to Omaha. I assume this is in Nebraska. I know Omaha is, well, I don't know. And we'll just say a distance of 300 miles. And now we have two journeys. That is, they're two parts of the trip. You know how these are all set up the same way. Part of the trip is on the bus and part of the trip is on the train. And here's what we have, and I'll do this in terms of a chart as we organize things. So we'll just say bus leg. We have a rate of 40 miles per hour. And then we have a train leg, and we're gonna say that there's no lapse in time. The train leg has a rate of 60 miles per hour. And lastly, the trip time is 11/2 hours, 5 1/2 hours. Okay, so we're going to organize this in a chart. And then, of course, this is just like the last problem. We'll say compute time spent on the train. So we're going to want that to be the simplest expression. We'll call that T when we set up our variables. So compute time spent on train. Now, just like the other problems, you can easily set these up and you can work these however you like. But for instance, say you're teaching this to a friend. We have D equals rate times time. So if we've got all these times, we can say T equals to distance divided by rate. So that, unlike the other problems, or actually like the problems, you have standard equations that govern how the arithmetic and algebra work. And with time, rate, distance, this one's a little bit more explicit. The equations we set up for fraction of work and mixture are based upon the problem, but they're always the same. And of course, this will always be the same for uniform motion problems. So now what we can do is I've got a little chart here. This is the only time I do a chart. Your choice. I think it does help to organize your work. With the other ones, we didn't really need it. What we had was sufficient. So we'll just say we have time, rate, and distance. My colleague Nate always thought that it was good when we had a book that used a chart for this, because he was a big fan of understanding with this, and I tended to agree with him. So with the bus, we have 40. And when we think about this particular situation for the train, we have 60. Now, this is what I was telling you about before to make it a little bit simpler. When we think of the time, we want the time spent on the train here. Let's just call that T. just so when we find t, we go right here and we don't have to do anything with it, just for simplicity. You don't have to do it, but it'll make it easier. And then, of course, the trip time here, total time is 11 halves hours. So this would be time on the bus would be 11 halves minus t. So this is where the chart is very useful in the sense that the organization maybe is a little bit harder to keep in your head, whereas here this is explicit. And then distance in this case will just be rate times time. So we have 40 times 11 halves minus t. And here we have 60t. So actually, I didn't even really need to solve for t here. I mean, that's good that you know how to do it, but based upon the logic here, this is going to be very simple because now, if you notice, we can now use the 300. That is, if we have the leg for the bus and the train, the two distances must equal in sum 300. So that makes it even easier. So by logic, we have 40 times 11 halves minus t plus 60t must equal 300. So again, if you write something down that you don't necessarily use, we obviously had to use that. No problem. Extra is good. So now when we look at this and we're thinking, well, we don't really have hard fractions here. Again, this too will absorb into the 40, so we won't even have any fractions. So let's go ahead and multiply this out. In this case, we have 2 into 40, which will give us 20. So this is 20 times 11 minus 40t plus 60t equals 300. Now, one thing that we can notice here, again, we've got a lot of extra numbers hanging out, which we can get rid of because we're lazy. So this will be 20 times 11 and add these two plus a 20t. And now if you like, there's a 20 in here. We know that 2 times 15 is 30. So this would be a 20 times a 15. Now notice this is where we can say, okay, well, we're just going to get rid of the 20s. So at this point, we can divide by 20. Sometimes it's good to just go ahead and write the 1 over 20 so you can remind yourself what you've done arithmetically. So now the 20s absorb. Well, wow, that's an 11. And then the 20s absorb. We have a t. And here the 20 absorbs and we have a 15. Well, that's the easiest equation in the world. So subtract 11 from 15, t equals 4. So we'll say this implies Wendy spends. Now, again, like I say, if you set it up so that you get the actual deduction of the problem for t, you don't have to make any other adjustments. Lots of times students will say, well, I found t, but if you go back to the chart, it's not describing the particular leg. You have to make an adjustment. So what I tried to do was just assign t to be the time that we actually needed. So Wendy spends 4 hours on the train. Now, like I said before, it is not required that you do a problem in a particular way. That is of no consequence as long as you have a legitimate way. The best thing about these problems is to allow the logic and the algebra to take over so that you can minimize the amount of computation. But again, that's going to take a little bit of getting used to, but it's certainly not required. I just know as you continue to work in pre-cal and we work at solving equations and we work into the trigonometry and apply that to the calculus, simplification is nice. Even in physics, we want to trim things down to the point so that we can see what's going on. And so when we look at this original equation, it's equivalent to this. And we were able to see that by letting the algebra do the work. Now, there are additional problems in your WebAssign, and there's some other examples that have to do with, again, time, rate, distance. I always recommend a chart. Sometimes you might have to do a problem just like we had in the previous with the time, rate, distance, where you end up with a quadratic. Okay, that will happen. So don't worry about the equation that ensues. Make sure with the time, rate, distance that you have some way of organizing the ideas. The time, rate, distance really, you can keep it all in your head, but it's nice to have some formulation of organization that you don't necessarily need for fraction of work or mixture. So try the chart here and see how that works for you. I think it does make for a nice organization that again is easy to teach, kind of like teaching Professor Ron's AC lemma. Okay. Now, what we want to do is say a little bit about how did we get 20 times 11 plus 20t? Okay, let me look at that. Oh, right here, notice when we subtract, we have negative 40 plus 60. That gives us the 20t right there. So these two sum to give us this, and then we just bring this down. Is that okay? Good deal. Let's check.
Yes, thank you. I didn't really see those like terms.
Yeah, yeah. Isn't that amazing? When you're doing math, this is what I tell all of my students. They like, Professor Ron, you sure do write down a lot. It's like my mind's freaking out. But again, you know, it's really interesting because as you work, your mind may play some tricks on you. And so what I would say is this: as you work these problems, make sure you put down enough information so you can actually go back and check your work. And kind of when you do this, that kind of reminds you. But that's a good point. I did this without kind of thinking about it to get that right there. So that's a good question. Yeah, you know, no part of the problem is unimportant, right, ladies and gentlemen? Unfortunately, as you work through this class, you'll see that you learn that in college algebra, and when you get to calculus, it's not over until it's over. And so, very good question. Now, what I want to do is talk about some fundamentals of inequalities. Your favorite pastime, right? when it comes to doing math, it's like if someone says inequality, everybody's like, well, let's pass on that. I like equations better. So what I want to do, and we will have a revisit of some of these techniques later in the course. I won't basically re-lecture on it. I think I may just assign some more problems for you to work on in chapter 3. But the inequalities do come up a lot, and the sign test that we will do, you've already learned in college algebra, but I want us to be able to do it with maybe a little bit of efficiency and in a way where we can use a number line so that we don't have to write elaborate charts. Sometimes students think, well, I've got to get an actual number. All we have to do in many cases is figure out plus or minus, and then we can move on. And that's going to save us a lot of time. So we'll just say in 1.8, we'll just say fundamentals of inequalities. And again, this will be kind of boring, so forgive me for the boringness, but fundamentals of inequalities. Now, of course, in the WebAssign, a lot of times they'll have you do a little graph where you know you plot the solution set, and again, just do that, you know, think of it visually. It's just a little extra problem that's a thorn in your side, but as we do number lines, you'll see that it's exactly what we get from the boundary value test. Now, first, we have a couple of theorems, and you know these theorems. This is something you probably learned back in general math. Your teacher told you and you believed because you wanted to get the correct answer. So for instance, here's something we use about the real numbers all the time, because the real numbers constitute a field and it's ordered. If we have two real numbers, we can compare them. We can always compare two real numbers. We can say A is greater than B, we can say A is less than B, or we can say A equals B. That's the law of trichotomy. The real numbers are very, very special because not only is the field complete, there are no holes in it, but every element is ordered. And that's why we do calculus on the real line. That's the main reason we focus on the real numbers. So if A is greater than B and C is less than 0. Okay, so you're thinking, this just means that it doesn't say anything about the sign of A and B. It just means that A is greater than B. It's to the right of B on the number line. And this just basically says, in terms of symbols, that C is a negative number. Any number less than 0 we call negative. Now we can say that the quantity A minus B is positive. We can also say that. We don't know any more than that, but A minus B here is positive. So that's another conclusion we can make if we know A is larger than B. But what I'm trying to show you here is that anytime we multiply or divide an inequality by a number less than 0, then the inequality reverses. So we would say that A times C would be less than B times C. And this is what you use often without thinking about it, or you just forget it. And then you wonder why your answer is incorrect. Because the real numbers form an ordered field, we have this very interesting theoretical result that says if you multiply or divide an inequality by a number less than 0, then the inequality reverses. So we'll just say inequality reverses. Obviously, if it's a positive number, there's no change. So we're thinking that we're going to solve inequalities like we solve equalities as long as they're not too complicated. But when the inequalities get more complicated and there are more opportunities for the expression to change sign, we have to be a lot more resolute as to how we come up with a solution set. So what I wanted to do is just say a little bit about why this is true. And then I'm going to give you the conjunction and the disjunction, and then a little routine to solve inequalities that you learned in college algebra. So for instance, we can say let script P be the set, just to get you thinking about this, be the set of positive real numbers. Positive real numbers. So when we think about P, if we drew the real number line, we would just have, sometimes we just use like a parenthesis here, or you could use a circle, and then we shade here, or make that darker like in WebAssign. So this would be P. All numbers, all real numbers greater than 0. That's what we call the positive real numbers. Now, one thing about the positive real numbers that we can assume are the following two axioms. Number one, if we have two positive real numbers, X and Y, then if we add them, the result again is a positive real number. We don't prove that, we just assume it. If you take two numbers that are greater than 0, that are real, then the sum will also be a positive real number. 2, if we assume that again we have two positive real numbers, their product will be assumed. I'll just put a little dot here, or you can just call it XY with juxtaposition, will be assumed to be a real number, a real positive number. So these are things that make intuitive sense to us. 2 and 3 are positive real numbers. When we add 2 and 3, we get 5. When we multiply 2 and 3, we get 6. We don't even think about the result of those cases as being anything but positive. So when we have a situation that's intuitively clear, kind of like axioms in geometry, we say, okay, we believe that. We believe that. We're not going to question that. That stands on solid logical ground. Okay, so what I want to do is use this concept to show why this is actually true. This is not an axiom. Notice here I have a theorem. This is not an axiom. We can actually prove this if we believe the axioms about the positive real numbers, and I think you do. So when we look at this, we'll say why about the theorem. We don't do, proofs we do when we want to understand why things work and how things fit together, like doing the modeling. We're not trying to beat ourselves up. We're just trying to say, can we dig a little bit deeper and understand what's going on? So now, like we have here, A greater than B equivalently says that A minus B is a positive number. That is, A minus B is greater than 0. What does that say? Let's just write it a different way. A minus B is a positive real number. So when you take an inequality and you subtract B from both sides, on the right-hand side, you get 0, and on the left-hand side, you get A minus B, and you automatically get that the difference is indeed a positive number. Now, let's look at what we have here. C is less than 0. But what does that say? Now, if C is less than 0, I might say, what does that say about its additive inverse? Okay, what is an additive inverse? What's the additive inverse of -3? You'll say 3, because -3 plus 3 equals 0. So if we have a number that's less than 0, its additive inverse must be what? A positive number. So this is going to say equivalently that the additive inverse of C is positive. And of course, we're going to use the fact that a negative times a negative is a positive. We can prove that too, but we can't prove everything. So I'm going to assume you know that. So in this case, the additive inverse of C is also a positive real number. So what I'm trying to get you to do, ladies and gentlemen, is think in terms of signs. There is no negative by the C, but we've assumed that C is less than 0. So you can't say, oh, well, C is positive because it doesn't have a negative. That's not true. We've assumed this. So that means the additive inverse, or the negative of C, in this case, is positive. So we have to think in terms of signs and what the symbols actually mean. So now, when we look at this inequality here, we should be able to take these two positive real numbers and use axiom 2. That is, if we take two positive real numbers and multiply them, then the result by 2 is also a positive real number. That is, the number should be positive, greater than 0. So we're going to use axiom 2. Again, I just want you to think about what it means to work with signs. So now we have A minus B times the additive inverse of C must be a positive real number, but that means that this must be positive. So by axiom 2, the product of these two positive real numbers is again a positive real number. So now we're going to use the distributive law, which we assume to be true. So we have A times the negative C. So that's going to be a negative AC. And then we have a negative B times a negative C. So that's going to be plus a BC. And this should be positive. So again, we're using the distributive law and a theorem that says the additive inverse times the additive inverse is the positive, okay? And now, obviously, what we're going to do, we're going to add AC to both sides. So equivalently, BC will be greater than AC by adding AC to both sides. And then, of course, you could write this first if you want, just take the mirror image. So AC is less than BC, which is exactly what we have there. So it is true. Again, you probably thought about this several times when you use this and think, well, you know, I believe it and I get the right answer when I use it. And when I don't use it or I ignore it, I don't get the right answer. So this is a theoretical result about real numbers that isn't always completely obvious to us. But and of course, at the time when your teacher told you this, you said, okay, I believe you. I'm not gonna question, I believe you. So now that you've gotten a little wiser and more educated, you can look at this and say it is indeed true that when I multiply or divide an inequality by a number less than 0, the inequality reverses. Now, there were just a couple of other things that I wanted to share with you and want to do a couple of examples. Here's another theorem, and you can think about the proof if you want. I think I beat you up enough with that one. So theorem. This has to do with the conjunction and the disjunction. And if you want to think about this on your own, that's fine. We'll use this enough that you'll actually remember it. So we're going to do the same thing we had before. We're going to start with the positive C like we had with the absolute value equality. So we're going to suppose that C is a positive number, again, which is opposite of this. And what we want to do then, and we're going to assume that X will correspond to an expression in X, like we do A and B with the identities. So the first one is called the conjunction. I'll just write it out, conjunction. And you'll use this so much in calculus that it'll be part of your vocabulary. And it's a very clean way to write symmetric intervals. We'll say more about this. So we would say that the absolute value of X less than some positive real number. Well, when it was equal to, we would have X equals C or X equals the additive inverse of C. When we have the inequality, we get a compound inequality. That is, we get X between the additive inverse of C and C. This is basically a symmetric interval about 0. So when you think about this, you have 0 here, and then you have negative C here, and you have C here. This is an interval that's symmetric about 0, and X lives in there. So we say that this interval is symmetric about 0. Interval is symmetric about 0. And we'll say more about this. But this is just a good way to get started with this. The idea is that at 0, we can go a distance C, and at 0, we can go another distance C to negative C. And of course, X lives somewhere in between the two. Okay, so this is termed shorthand notation. convenient. Lots of limits in calculus are written with this notation of the conjunction. And then you spread it out, so to speak, interpret it by the compound inequality. Okay, so this will be something we'll get plenty of time with. When you get to calculus, you maybe wish you'd never seen it. And then the second one is called the disjunction. Disjunction. And the only difference is it doesn't get as much time as the conjunction. This just says that the absolute value of x is greater than c. And then, of course, instead of getting a connected set, you're going to get a set that's disjoint, that's disconnected. The intervals will go in opposite directions. So this would say that x is greater than c when it's true, or x is less than the additive inverse of c. So what we get is broken up, so to speak. So we have a c here. We've got 0 in between, and then the additive inverse of c. And so what we have are infinite intervals here that are disconnected. So when we think about a disjunction, we think about a set that is disconnected. For instance, the absolute value of x is greater than 5. So we would have 5 to infinity and then negative infinity to negative 5. So again, this is a shorthand. This is more of an interpretation. So you may have seen these before, and if you haven't, that's okay. We'll spend enough time with these so that they're comfortable. The main thing here is that absolute value is a very useful function that helps us to create intervals that are useful in studying calculus and analysis. And so this is why when you get the definition of the limit of a real valued function, it will utilize the conjunction twice in the hypothesis and the conclusion. So the idea of the definition, the idea here is this is a very useful notation that obviates the need to write the compound inequality. This, and you're going to look at this, and the light bulb's going to come on, and it's going to be better for you in all possible situations. So again, there'll be more of this as we work through this class and as we work into calculus. Okay. Now, what I wanted to do is take the idea of solving inequalities. So when it comes to actually working with an inequality, let's take something simple like a quadratic. For instance, here's an example. The WebAssign would say solve in the real numbers. And so maybe we had the following: 5x squared plus 3x is greater than or equal to 3x squared plus 2. Now, when you think about this, excuse me, when I run in the mornings, plenty of allergies, but that's okay. That's why I live in Texas. I love the temperate weather, but there's lots of stuff floating around. So when you look at this particular example, you're thinking, okay, well, I could start guessing some numbers. But when it comes to working with real expressions, we know that we can always compare things to zero. That is, if we have an expression and we're comparing it to zero, we can do a sign analysis. So what we want to do with an expression like this or inequality is to remove all of the terms to one side and create a zero. And then once we create the zero, we want to be able to analyze the sign of the resulting expression. So first, let's clean this up. And so we'll have 5x squared minus 3x squared plus 3x minus 2. So we're going to take everything over here and subtract it. So this gives us this. So at least when we look at this, we want to be able to compare this expression to 0. That is, we'd like to be able to know, when is this expression 0, which is basically solving an equation, and when is it actually positive? So this is where we have the idea of boundary value. Now, first, let's go ahead and combine some numbers here, or some terms. So this will give us a 2x squared plus 3x minus 2 is greater than or equal to 0. So when you look at this, you think of what we call a boundary value. Now, what's a boundary value? This is actually a function, but when we think of the boundary value of an expression, we think of real numbers for which it is 0, and then we think of real numbers for which the actual expression is undefined. So we'll just say this: let f of x be an, or just a real expression in x. A real expression in x. Then x element of R is a boundary value. We'll just say boundary value. Sometimes we just call that BV for short, if and only if. Number 1, f of x equals 0, or 2, f of x is not defined. And that has to do with asymptotic behavior. That is, the function or expression may become infinite or unbounded. Why is this important? Because for these particular values, these particular real numbers, the sign of the expression could change. Doesn't necessarily have to. But when we're trying to figure out when a particular expression has a given sign, then we need to understand where the sign can possibly change. And so now, when we look at this, we just say, oh, okay, well, this is just a quadratic polynomial. It's never going to be undefined, so to speak, but possibly could be 0. So let's check for BVs with number 1, whereas 2 would not be something we would consider in this case. But now you can see AC. AC is 2 times a negative 2. Now, of course, that's 0, so that's no good. So let's just think of this as a negative 4 and say 4 times a negative 1. And that'll give us the 3 that we need. So again, the 2 and the negative 2 give us a 0, which isn't very useful, but we're thinking negative 4 can be written as 4 times a negative 1. And then, of course, the sum of those two numbers is 3. So we get 2x squared plus 4x minus x minus 2. So just Professor Ron's AC lemma. And now we can factor by grouping. So we'll take a 2x here. Very simple algebra, but important algebra. Just like doing the modeling problems. And then, of course, we can extract a negative 1 here. So now we can factor. We have x plus 2, and we have 2x minus 1. So now we think of f of x here as being this expression that's factored. And so now by 0 product, this will say BVs, if and only if x plus 2 equals 0, or 2x minus 1 equals 0. So of course, that'll be x equals -2. And then of course, if we add 1 to both sides and divide by 2, we have x equals 1/2. Now, when you think about your work in college algebra, you're thinking, oh yeah, I mean, we can think about multiplicities of zeros, but even if you don't think that, it's still a simple process. We see that we definitely have two boundary values. One is -2 and one is 1/2. And that's clearly where f is 0. And we know that we need 0. So this is where we can draw a number line to keep our lives simple. So we can have a -2 as a boundary value, and we can have a 1/2. Just space it out so you have plenty of room. Now, one thing that we can notice here, you can take test points, but this is a polynomial that's quadratic, and we know that it's going to become positively infinite as x approaches infinity or negative infinity. But you can just say, okay, well, let's just go ahead and write here x plus 2, and we'll go ahead and factor the 2 and write that as x minus 1/2. So we can take this expression and write it here, and we can check it out. So we can say a -10 as a test point. We could say a 0 as a test point, and a +10, just any choice of test point that lies in the interval. And then, of course, you can say here the negative here in this term or this factor will be negative. The -10 in here makes that factor negative. Negative times a negative, positive. Of course, you expected that. That gets a check. Now, of course, -2 makes the expression 0, so that gets a check. So is 1/2. But now, of course, 0 here, when you replace 0 here, the expression is positive. But when you replace 0 here, the expression is negative. Positive times the negative is negative or less than 0, so that doesn't work. And then, of course, what you expected above, below, and then above. If we try 10, we get plus for the first factor and plus here. Notice I don't really, it is of no consequence to me what the actual value is. I just want to know the sign. And so again, the plus times the plus is greater than 0, again, positive, so that gets a check. So when you think about this, this number line replaces the chart. You can do the factored version here and then keep track of the factors above the region without having to draw an elaborate chart. And this gives you all the information you need. And so now you just follow the checks. So this implies, or equivalently, x lives -infinity to -2. So this is going to give you good practice typing the interval notation. And of course, remember -2 must be included. So you use a bracket because it makes the expression 0, which is part of the inequality. And then of course here, we don't have any of these numbers, but then we can start at 1/2 and march to infinity. So we'll do a union symbol, union, just the U you can use from your little math palette. And then 1/2, which we include with the bracket, comma, infinity. So what's important here when you think about this problem is that this is going to recur over and over. And in some cases, what I'll do is think about multiplicities. It's like above, below, and then above. Because if you look here, these zeros have multiplicity 1. So the sign must change at these numbers. I mean, at least in terms of a small neighborhood. So when you think about a neighborhood of -2, the sign will have to change on either side of that number. Likewise here, because the multiplicities are 1, that is an odd number. There's no way that you can hit the axis and then bounce back up. That would require even multiplicity, but you don't even need to know that like right now. You probably already do. You can just do this very simple sign test. And again, if you're working with functions that you can see in your brain, you won't even have to worry about this. I will suggest this. When you're working with more complicated expressions, especially when you have variables in denominators, it's best to be very careful about how you check the sign, because you can make a little slip and then throw the problem off. But that's okay. Again, inequalities take on all kinds of expressions and forms. Like when we think of the conjunction and the disjunction, that seems to be really far away from what we just did. But when we think about something like this would make a good calculus problem or a good pre-calc problem, where we would really want to know where this function actually had non-negative values. So in your WebAssign, again, you're going to think of, if you did the number line, you could think of including the 1/2. So maybe you did a disk or a bracket. And of course, here you could have a disk and a -2, and then the darker here shading. Sometimes WebAssign will direct you to graph the solution set, the one-dimensional solution set like that. But of course, this is probably the preferred. Again, this is just a little extra, probably not as important as being able to write the interval notation. So as you work through this and remind yourself of it, we'll do more examples of this on Thursday, and then we'll talk about functions in general. But as you look through this, compare what you've done in the past. You don't necessarily have to do an elaborate chart here. Take what you already know and maybe add a little bit to it. Sometimes these are called cut points. I just call them boundary values. What you choose to call them is completely up to you. And like I say, we'll do some more exercises with this and then talk about functions. Now, remember, I will send out invitation for conference hour. Yesterday, I'll have a earlier conference hour, and then I'll have a conference hour in the afternoon. So I'll send out email invites for that, which I'll do every time during the week. And so if you have some questions about your current homework or questions about what we've been doing, please stop by, communicate with each other. If you have a question that you want to send via WebAssign, do that too. I enjoy getting messages from you. It's good to see that you're working, and just keep track of the due dates on WebAssign for your homework. Your first set of homework is coming up at 11 p.m. on Wednesday. And then of course, the first quiz, 11 p.m. on Thursday. Now I'm a stickler for meeting due dates, basically because I want you to stay current. And I'm giving you that cushion of time into the following week after we lectured on it to ask questions and to complete that. But it's important that we stay current, because with all of these STEM math classes, we cover so much material. And I don't want you to be in a situation where the understanding is less because you haven't stayed current. So as I've reminded a lot of students who come to office hours or the conference hours, do some math every day. Knock out a few problems every day so that you don't just arrive at a day during the week and you've got tons of problems to do. That is unnerving, and it makes you feel like, oh, I can't do this. You probably are very capable, and many of you can knock out a lot of problems in a little bit of time. But I do want you to have a little bit more time to think about the work as you progress through the class. So I appreciate your attendance today. Again, I'll send out invitations for the conference hours, and I look forward to seeing you. If I don't see you at the conference hour, I'll see you at our next lecture. So enjoy the warm weather while it lasts, and everybody have a good day. Thank you. Thanks again for your attendance. Thanks, Professor Ron. That's very kind. You all are the best students in the world. Don't let me down, okay? I know that I'm asking you to do a lot of work, but it's going to pay off when you get to the calculus. So everybody have a great day. And thanks again for your kind remarks.